Hello everyone! In this video we will continue to examine topic 5.4, the magnetic effect of electric currents, and in particular we will return to our very first topic and discuss the magnetism of a bar magnet and the formation of an electromagnet. So, there's a phenomenon known as induced magnetism, which we've mentioned before. Okay, this is temporarily induced magnetism in particular kinds of materials, right? Materials known as ferromagnetic materials. This induced magnetism is always attractive. So the classic example is a magnet brought close to a refrigerator or some other piece of iron, or nickel or cobalt. And the result of this is that as that magnet is brought close, you can think of the poles, okay, in quotes, of the components of the refrigerator as orienting, okay? Just like with a charged electric balloon, you can get some polarization in a wall. You can get a similar effect with magnetism. So you can think of the wall as being formed of sort of these miniature magnets which rotate and line up and then produce an attractive force between the external magnet and the ferromagnetic material. But what actually is going on at a microscopic level here? It's not at all clear, and there's far less of an ability to simply wave our hands at it than in the electric case. So fundamentally, it's actually pretty important to say just a little bit more about what's happening inside that material. And it can be explained, at least in part, and at a first glance, so this isn't a perfect explanation, but it can be explained by considering the molecular structure of the material. So what I want you to do is consider an atom, an individual atom, as basically composed of a simple current loop. This is not a perfect analogy, but it's not bad. If you have a simple current loop, okay, a simple current loop simply composed of an electron in orbit around a nucleus, then that will produce a magnetic field the way any current loop would. And in fact, you can orient that magnetic field, if you have a current loop, by considering the direction of that field as it goes through the loop. And if the electron is orbiting the proton here, you can draw an arrow representing the magnetic field through that tiny little current loop as being a little bit of a north pole and a south pole. And this right here, this representation of the magnetic field of the orbit of the electron, or as it turns out, a property called the spin of the electron, is the magnetic dipole moment. This is not required for the IB, but is useful in sort of explaining what is going on with induced magnetism and with magnets in general. This magnetic dipole moment is a vector that points from south to north here, just the way the magnetic field inside a magnet would. And it's a vector that points from south to north that would experience a torque. A small torque in a magnetic field, that rotating or that rotational force. And so what's happening fundamentally inside is that at a molecular level, a whole bunch of the atoms are all aligned with one another in what is known as a domain. So just like we saw that current-carrying wires sort of orient together, they feel a force that pulls them to be aligned, and we saw that small magnetic dipoles are aligned with an external magnetic field. That's what a compass is. Then the individual components of the iron also align sort of within the domain. Now, there are sort of, in a macroscopic material, because you're talking about trillions of magnetic dipole moments, you'll have sort of regions where all the dipole moments are aligned this way, but also regions where the dipole moments are aligned this way and this way. And this happens at a scale that is at sort of the microscopic but not atomic or molecular level. So we're still talking trillions of atoms in the same direction, but these regions are still microscopic. So we're still talking about millimeter or micron-sized regions or thereabouts. These regions are known as domains. So the domain is a region of matter in which the magnetic dipole moments align. In a non-magnetized but ferromagnetic material, the reason it's not magnetic is because those particular atoms and molecules have all their domains sort of willy-nilly misaligned in different directions. But if you magnetize that material, if you expose it to an external magnetic field of any kind, then all those domains align, and suddenly the magnetism of each of the domains reinforces each other, and you get a full magnet. Okay, so for ferromagnetic materials, this is what happens. Other materials exist, and I'm not going to go into it in detail. All right, so this little metaphor here is a good way of understanding exactly where these domains come from. It's not perfect, and really it has to do with the spin more directly. But this is why, if you've taken chemistry, electrons are represented as having up and down spin in the same state. Okay. In any case, induced magnetism occurs when a ferromagnetic material is exposed to an external magnetic field. This happens with the refrigerator, with the compass, as we discussed, and with an electromagnet. And is the end of the explanation for why an iron core added to an electromagnet sort of reinforces the field. So all these domains align with the external field provided and reinforces the solenoid field, giving you a pretty powerful electromagnet. This also fundamentally explains, notice, with reference to a current loop, the origin of material magnetism. So a bar magnet is a material in which all these domains, made up of these tiny little current loops, all oriented in the same direction, line up. So there's no current going through the bar magnet, not fully. It's just that the materials inside the bar magnet can all be thought of as these tiny little current loops of the charged particles that compose them, and they all align in ferromagnetic materials, making a permanent or semi-permanent magnet.